Okay. Testing. Testing. Hello. Okay, mic works. Why does the character move so slowly? I think we're fine. Hi. Wow. It's pretty late again. But hey, I'm getting back into streaming, so please be nice to me for a bit. And yeah, let's do today's learning. I don't know if I remember what we learned yesterday. I know it was about tokenizers. Oh yeah, the QA pipeline where I thought it meant quality assurance, but it meant question answering. It was mostly about application, about truncation of long text. Yeah, I think I had fun. So for today, the way I see it, it might not be that long. I feel like each one of them is like blog post, and so since this is not that long and I don't have that much time, I'm thinking I'll watch some of the lecture because it's been a while since I've watched the lecture. So that's the plan for today. Yes. All right. Let's do this. Normalization and pre-tokenization. So stuff we do before we tokenize. I like that. Okay. Before we dive more deeply into the most common subword tokenization algorithms used, with transformer models, byte pair encoding BPE, word piece, yes, and unigram, less so. I think less so. We'll take a look at the preprocessing that each tokenizer applies to text. Okay, what tokenizers do to text as preprocessing. Are tokenizers supposed to do preprocessing? I thought they don't. I mean, I don't know, maybe there's a really high chance that I've already studied this and I'm out here thinking, do they do this? Forgetting everything. Yeah, getting into old ages like that. Here's a high-level overview of the steps in the tokenization pipeline. All right, how are you today? Becomes, oh yeah, okay, so we, today, why is it today? Oh, because it's texting, all right. The U becomes smaller. That's case, uncased. And then segmentation. It's called segmentation, right? And then adding code, more segmentation. Yes, more segmentation. Segmentation part 2. And then this part is called the normalization. This is pre-tokenization. This is tokenization using the model style. Got it. And then post-processing. This is our output. Nice. Before splitting a text into subtokens according to its model, because there are different styles, who was it that was using SML? What is SML? HTML. HTML style. Tags. Yeah. Tokenizer performs 2 steps, normalization and pre-tokenization. Right. Let's see, what is normalization?
In this video, we will see together what is the normalizer component that we find at the beginning of each tokenizer. The normalization operation consists in applying a succession of normalization rules to the raw text. We choose normalization rules to remove noise in the text, which is useless for the learning and the use of our language model. Let's take a very diverse sentence with different fonts, upper and lowercase characters, accents, punctuations on multiple.
How is this a sentence? This is no way. Like this part, the E and the... This is not a sentence.
Spaces to see how several tokenizers normalize it. The tokenizer from the FNet model has transformed the letter with font variants, or circled, into their basic version, and has removed the multiple spaces. And now,
Whoa.
if we look at the normalization with Retribet tokenizer, we can see that it keeps characters with several font variants and keep the multiple spaces, but it removes all the accents. And
Right.
if we continue to test the normalization of many other tokenizers associated to models that we can find on the hub, we see that they also propose other kind of normalization.
What can you do about fonts? Wow.
With the fast tokenizers, it's very easy to observe the normalization chosen for the currently loaded tokenizer. Indeed, each instance of a fast tokenizer has an underlying tokenizer from the HuggingFace tokenizers library stored in the backend tokenizer attribute. This object has itself a normalizer attribute that we can use thanks to the normalize string method to normalize a string. It is thus very practical that this normalization, which was used at the time of the training of the tokenizer, was saved, and that it applies automatically when you ask a trained tokenizer to tokenize a text. For example, if we hadn't included the Albert normalizer, we would have had a lot of unknown tokens by tokenizing this sentence with accents and capital letters.
Right.
This transformation can also be undetectable with a simple print. Indeed, keep in mind that for a computer, text is only a succession of 0 and 1, and it happens that different successions of 0 and 1 render the same printed character. So 0 and 1 go in group of 8 to form a byte. The computer must then decode this sequence of bytes into a sequence of code points.
Okay.
In our example, the 2 bytes is decoded using UTF-8 into a single code point. The Unicode standard
I love UTF-8. Okay.
then allows us to find the character corresponding to this code point, the CCDLA.
Isn't this ch in Turkish?
Let's repeat the same operation with this new sequence composed of 3 bytes. This time, it is transformed into 2 code points, which also correspond to the CCDLA character. It is in fact the composition of the Unicode Latin small letter c and the combining cedilla. But it's annoying, because what appears to us to be a single character, it's not at all the same thing for the computer.
Isn't it capital and small? Oh, that's why we do normalization, obviously. Duh. Duh me, not duh them. Okay.
Fortunately, there are Unicode standardization standards known as NFC, NFD, NFKC, or NFKD that allows erasing some of these differences. These standards are often used by tokenizers. On all these previous examples, even if the normalization changed the look of the text, they did not change the content. You could still read, "Hello world, let's normalize this sentence." However, you must be aware that some normalizations can be very harmful if they are not adapted to their corpus. For example, if you take the French sentence "un père indigné," which means an indignant father, or normalize it with the bird-based uncast tokenizer, which removes the accent.
Right.
Then the sentence becomes "un père indigne," which means an unworthy father.
Whoa. Meaning lost. Yeah, I don't want accents removed from... Accents matter. That's different. I mean, Isn't Bert trained on English only?
If you watched this video to build your own tokenizer, there's no absolute rules to choose or not a normalization for a brand new tokenizer. But I advise you to take the time to select them so that they do not make you lose important information.
All right. That was interesting. But the question is, if we have accents, then we don't use something that takes them away. Especially if they matter and not they're there for fun. Oh, hi. Hi. Hi, Silent Mike. I don't know why I keep calling you Mike when it's written Michael. Michael, what's up? I love the fact that each time someone posts the waving hand on YouTube, it shows as pink hand waving. Oh, hand pink waving on up there. Yeah. So hi. We are learning about what tokenizers do before they tokenize technically. I mean, parts of tokenization. So there's a normalization step that involves general cleanup, such as removing needless wipes. Oh yeah, white space, that's true. You know what? I'm very sure I've done all of this by hand, and now I feel cheated. But I guess that was a while ago, so less cheated. White space, lowercasing, and or removing accents. That's an and or because accents matter like a lot of times, because bringing back the Turkish example, because that's the only thing I can think of, accents change the sounds, just like I'm guessing French. So when you change a letter, you change the meaning. If you're familiar with Unicode normalization, am I familiar with Unicode normalization? I don't think so. But like I know what's Unicode because you have to use it. What does it do? Describes normalization for Unicode text when implementations keep strings as in. Implementation keep strings in a normalized form. They can be assured that equivalent strings have a unique binary representation. She just talked about that. Examples, additional specification regarding normalization of Unicode text and information about conformance testing for Unicode normalization forms. Okay. I mean, in a way it has to be, but like NLP, it's focused on text, right? NLP also includes audio, so that part I don't know how that's normalized though. But like the easiest one is like you saw up here, or maybe you didn't. The capital to small, like that's normalization. So I'm sure in machine learning, because NLP is a subfield within machine learning. So the answer is yes, has to be the same, I think, based on the knowledge that I have as of this moment. Because if I sound too confident and then I'm wrong, then I feel bad. So the HuggingFace tokenizers, transformers tokenizers, has an attribute called the backend tokenizer that provides access to the underlying tokenizer from the HuggingFace library. So we have the backend, and okay, it's a class, okay. The normalizer attribute of the tokenizer object has normalized string. So you say backend tokenizer and you can work with it and choose like select parts. I guess I don't need this one because I finished it yesterday. Let's open today's collab and walk with it. So you can give it something fun and it makes it less fun. it takes the flavor out of sentences. That's fun. Let's take hello, how are you? And make it Turkish because I feel like testing it on Turkish. I have no idea. What's hello in Turkish? Help. Oh, that's it? That's not enough. But I guess if I just add it at the end, okay. It's supposed to be Nasılsın? Oh God, my Turkish is horrible. You know what? Let's not even try. Nasılsın? Ugh, I forgot. Anyway, all right, do that. And then, yeah, you can normalize it, like explicitly choose to normalize the text, which is pretty cool. Since we've picked the bird uncased, which means it makes it small, applied lowercasing, removed accents, we can try the cased version to see what happens. Sure, I can do that. I can have two different models. Tokenizer 1, tokenizer 2, and then we can have cased and uncased. How about that? What? There's an error. And then we copy and paste through. We have tokenizer 2's backend tokenizer. I'm hoping this will all run because I ran it and then no. Yes. No. Well, I'm gonna try again. All right. So let's see the difference. One is capitalized, removed. It didn't know what to do about this I. This I doesn't exist in the English language. I mean, it just kept it. Okay, I'll keep this in my text. I like it. I want to confuse the tokenizer. This time we do pre-tokenize, which is separation. I'm curious if it's not. Okay, it's not separated, which good. But the oh wait, shoot. Does it matter if I try cased uncased? No, it shouldn't now. The only thing about it is cased uncased. Let me read this thing. Oh, well. Oh, there's another video. Okay, sure, why not? Oh, hi JSS. It's been a while on my side. Hi. Yeah. I am trying to come back and learn stuff. How is life going on your sides? Whoever is here in the chat and is willing to talk. Because when someone's name starts with the word silent, I tend not to ask too many questions. I don't know if that's me assuming.
The tokenization pipelines involve several steps that convert raw text into numbers. In this video, we will see what happens during the pre-tokenization step. The pre-tokenization operation is the operation performed after the normalization of the text and before the application of the tokenization algorithm. This step consists in applying rules that do not need to be learned to perform a first division of the text. Let's look at how several tokenizers pre-tokenize this example. The GPT-2 pre-tokenization divides the text on spaces on some punctuation, but not on the apostrophe. We also notice that spaces have been replaced by a capital G with a dot above. Albert's pre-tokenization divides the text at the level of spaces, adds the space at the beginning of the sentence, and replaces
it didn't separate even. Oh, wow.
these spaces with a special underscore. Finally, Bert's pre-tokenization divides the text at the level of punctuation, on spaces. But unlike the previous tokenizers, spaces are not transformed and integrated into the tokens produced with this pre-tokenizer. Through these three examples, we could observe the two main types of operation brought by the pre-tokenization. Some change on the text and the division of the string into tokens that can be associated to words. Finally, the backend tokenizer of the fast tokenizers also allows to test the pre-tokenization operation very easily thanks to its pre-tokenized string method. We notice that the output of this operation is composed of both tokens and offsets, which allow to link the tokens to its position in the text given in input of the method. This operation defines the largest tokens that can be produced by the tokenization, or, in other words, the barriers of the subtokens which will be produced then. And that's all for the key characteristic of the pre-tokenizers.
So, segmentation. We did normalization and now we do segmentation. As we will see in the next sections, a tokenizer cannot be trained on raw text alone. Instead, we first need to split the text into small entities like words. Or smaller if possible. Okay. Don't even remember why I added this into my username. It makes it feel ominous. I just thought you prefer to be in the background. That's why I never ask you too many questions. Hello, hi. What do you do? What is your background mostly? Because are you working professional or a student? And if you've answered that before, I'm sorry. I have a memory of a goldfish sometimes. Not always. I remember silly things, you know? That's where the pre-tokenization step comes in. As we saw in chapter 2, a word-based tokenizer can simply split a raw text into words, right? On white space and punctuation, which is super basic. Those words will be the boundaries of the subtokens the tokenizer can learn during its training. All right. But even you're teaching a tokenizer to learn word boundaries, but you are giving it the word boundaries. I don't know. I'm lost. I know each type of tokenizer splits on text differently. How do you know it's what you want? I don't know. To see how a fast tokenizer performs a pre-tokenization, we can use the pre-tokenize stir method for the pre-tokenizer attribute. Last time we were using the normalizer attribute. Now we're using the pre-tokenizer attribute. I don't think we'll see a difference between tokenizer 1 and 2, but let's see. Go. Oh, shoot. All right. You go first, and then you go second. Are they the same? Yeah, Yeah, because they're both Bert. We had like Albert and stuff, then that would be different. Cool. Ooh, from GPT-2, now we're getting GPT-2's tokenizer, and it's different. I'm still gonna put my Turkish word in to see how it will be dealt with. Alright. Ooh, what is happening? Oh, I don't know if you can see, so I'm gonna zoom in. But like, it recognized that the eyes are just different, so it turned it into. I love each time I'm seeing this G, I'm reading it with it, like Gao, Gare. Coolsies, that's pretty cool. Oh, T5? Ooh, I love T5. Let's see how T5 works with it. Oh, I forgot to add my Nuslison. I think it's Nuslison without the L. Should I check Google? Oh, I closed it. Oh well. You don't care, and I'm happy for you about that. You don't care about punctuation, while you do. Okay. Notice how the tokenizer is already keeping track of the offsets. Yeah. I did notice. Which is how it can give us the offset mapping. We used in the previous section. Here, the tokenizer ignores the two spaces and replaces them with just one. Oh, we have a two space. I did not notice. But the offset jumps between because obviously, right. 14 becomes 16. I see. So that it can be accounted for. Since we used a BERT one, and it splits on white space and punctuation, others are different, like GPT-2 splits on white space, punctuation plus. That's it. Oh well. But we'll keep the spaces and space becomes the G symbol. I thought it's the start of student and working, so both. When I wake on time, I get to watch your stream while having. Oh, that's so cool. Yeah, if I also wake up on time, I can do the streams. And if I wake up late, I don't have the time to do the streams, so that's nice. That's nice that we technically can have coffee together because I have my coffee here with me. Good luck on the student part. I don't think I can help, but do let me know if there's anything I can help with. Bachelor student or higher, like, because bachelor student and working might be, I don't know, would it be harder? Because I think it would be harder. But if you're working in your field, then I think it would be easier for you to blend them together and learn from each side. I've done, I used to, like when I was a student, I did summer internships, which is not really working. Yeah. Enabling to recover original space. That's smart. Note that unlike BERT, this tokenizer does not ignore the double space. It just makes it its own thing. Did we have that here? Yes, we did. And I did not notice. Alright. For the last example, we're using T5, which I think is a Microsoft model. It's an all-purpose model, not really, but like it does ASR and text-to-speech and translation, I think. Just like Whisper. Whisper does ASR and translation. They get free work from interns. true. I did get paid for one of the tasks that I helped with. So like if the task is valuable, you get paid for it. If not, you're just learning from them. So it's a mutual, depends on the place, honestly. Some places are less ethical. Okay. Sentence piece algorithm. I see. Which just does space, the way I see it. No? Like the GPT-2 tokenizer, this one keeps space, replace them with the underscore token, but the T5 tokenizer only splits on white space, not punctuation. And did it ignored? Oh, there's no space there. Added a space by default at the beginning and ignored double space. So it did not make a double space here. Cool. Now that we've seen a little of how some different tokenizers process text, we can start to explore the underlying algorithms themselves. We'll begin with a quick look at broadly, widely applicable sentence piece. Then, yeah, get paid. Experience is really worth value of currency. I agree. For students, experience matters in this society. Experience matters for you and for your career. Yeah, it's good being among good people. Oh my god, I just had a flashback to my dream, my last night's dream. That's weird. Okay. Explore the underlying algorithms themselves. We'll begin with a quick look at the broadly. Oh, I said that. Then over the next 3 sections, we'll examine how 3 main algorithms used are the 3 algorithms used for subword tokenization work. There are, like the BPE is the one that I've seen everywhere. Byte pair encoding, word piece, and unigram. I love unigram. I just love anagrams. All right, I like that. I mean, I'm not gonna study them today, but I like that. Oh yeah, I always remember ISS as well. Yeah, actually, during yesterday's stream, there was a person who is a physicist, and I dream deja vu. You're like, oh my god, did I have this dream? Like something makes you remember it, which is fun. Yeah, with the physicist, I did not talk about ISS, which I'm now sad about. But I did geek out about stars and the moon. Good stuff to geek out about. If you see, or if there's time, I doubt there's time. But around sunset and then a few hours after, the moon is in the sky, and it will be a 5-day-old moon. I know about how old the moon is because Arabic calendar is based on it. I'm not using the Arabic calendar, but it's something that I like. I have it on my screen. What? Lock screen? Yes, my lock screen background shows the Arabic calendar. So I know what day it is. I also forget my dreams when waking up, but you know the deja vu stuff you have? You're like, someone talks about something, and you're like, where did I, what? That part happened. Oh, you saw it. Amazing. Yeah, it did look beautiful. I saw it yesterday as well, and I'm looking forward to it today. I have this app that tracks, like, there are multiple apps that track, but there's the one that tells you it rises in that, like, in an hour or like in 30 minutes. So that makes me look forward to it and try to find it during the day. Because, you can like start seeing it I don't know, depending on where you are, but probably like afternoon, early afternoon. Yeah, super early afternoon, depending on where you are. I watched this crash course thing about astrophysics, and there was a video explaining how the moon cycle. And since then, I can tell when you can see the moon and where it is. It's just like it's a schedule. You can memorize it quite easily. Okay, I'll say one thing and I'll shut up. When the moon is full, when the moon okay, fine. I think it's a Muslim thing. When the moon is like 1 day old, it sets with the sun and rises with the sun. So like you can barely see it. When it's like 7 days old, it rises. Help me. Rises with sunset. And then when it's 14 days old, I think 14 days old, it rises with sunset. What's wrong with me? Oh, well, I forgot everything. But no, I do remember. Yeah, when it's full, rises with sunset, and it looks beautiful. Anyway, you get the point. 7 days is midway. Rises when the sun is halfway in the sky, so noon. And then when it's 21 days, it probably rises around midnight. There. Now I can shut up. So then you can see it in the morning and stuff like that. You can see the moon in the morning after, like, it's like 20 days, stuff like that. Sentence piece. That's a thing. It's a tokenization algorithm for preprocessing of text that you can use with any of the models we'll see in the next 3 sections. Really? So it's a thing that happens before. Or it considers the text as a sequence of Unicode characters and replaces them with the underscore character, used in conjunction with the unigram algorithm. We'll see that later. Doesn't even require pre-tokenization step, okay? Very useful for languages where, really? Space character is not used like Chinese and Japanese? Whoa, how? Doesn't it split on space? That's odd. The other main feature of sentence piece is reversible tokenization. Yeah, because you can see the space that's there. There's no special treatment to spaces. Decoding the token is done by concatenating them, replacing the underscore with space. This results in the normalized text, as we saw earlier, because Bird removes space and tokenization is not reversible. You have to do it yourself by hand. Cool. All right. Algorithm overview. In the following sections, we'll dive into the 3 main subword tokenization algorithms: BPE, used by GP2 and others; word piece, used by BERT; and unigram, used by T5. Is it? Cool. Before we get started, here's a quick overview of how they work. Don't hesitate to come back to this table. Got it. BPE the training starts from a small vocabulary and learns rules to merge tokens. Word piece starts from a small vocabulary and learns rules to merge tokens, so everybody does the same thing. Training step merges the tokens corresponding to the most common pair. I don't know what that's supposed to mean. Merges the tokens corresponding to the pair with the best scores based on the frequency of the pair. Okay, frequency makes sense. Isn't that unigram though? Privileging pairs where each individual token is less frequent removes all tokens in the vocabulary that will minimize the loss computed on the whole corpus. Learns merge rules and vocabulary, just vocabulary with a score for each token. Yeah, I know that part. Encoding splits a word into character and applies the merge learned during training. Finds the longest subword starting from the beginning that is in the vocabulary, then does the same for the rest of the word. Finds the most likely split. You can't see that because of my head. All right. Into tokens using the scores learned during training. Yeah, I think I only got the unigram one. Word piece sort of makes sense, but BPE, I am not there yet, and that's why we're going to study it in the next lesson, which is not today. We have around 20-ish minutes, so we're going to look at this lecture, and since it's been
also is when I say
like more than a week since I watched this, I know it's about prompting. When I was like just moving around, I remember, yeah, output stuff, answer, okay, yeah, I've forgotten. Oh well.
few-shot prompting and in-context learning. These are basically...
Is the audio too low or is it decent?
The same thing. They basically refer to the same concept, but just from slightly different examples. Slightly different angles. Few shot is in contrast to zero shot. So zero shot means you're providing no examples. So zero shot prompting, you would have none. Few shot, you have several examples. In context learning means that you're learning how to do a task, but instead of providing the model with fine-tuning data, you're providing the examples in the language model's context. So they both basically mean the same thing, but they're just contrasting to like either a zero shot or fine-tuning, which is why the terminology is different.
So if they're having a user-facing interface, and can you do few-shot prompting for the rendering?
Yes, you can definitely do few-shot prompting. I'm actually going to talk about exactly how you do this in like an OpenAI model.
What's few-shot sampling? Does it mean like getting a list of answers?
Here, which is for OpenAI models, there's a couple ways that you could do this. One way you could do this is you could have the role be user and the role be assistant, and just add like additional conversational history into the messages that you're sending to the language model. But actually the recommended way of doing this, which is in the OpenAI cookbook, which is in the reference, is that you send this as a system message, but you provide this like additional name variable here, with example user and example assistant. The main reason why you do this is just because if you don't, if you send it in as the like user and assistant, the model might refer back to the few-shot examples as something that happened previously in the conversation. Whereas if you send it in the system message, it's guaranteed to not do that. So I think it's like less of an accuracy thing. It's more of a like, it's more of a prompt privacy.
Oh, I was about to say it's more of a training thing, but privacy
thing than anything else. So this is a recommended way of doing this. On the other hand, if you're using like an open source model, you need to be careful because this name might not even be included in the prompt template. Like for example, in the light LLM prompt templates that I was sending in, this is not even included at all. So you might just get a weird system message that is poorly formatted. So you need to be a little bit conscious of that. Cool. Any questions here? Does that answer the question? Cool. Okay. So one thing to be aware of is LLMs are sensitive to small changes in the in-context examples that you provide to them. So previous work has examined this from a number of angles. There's a paper by Liu et al., and they examine the sensitivity to example ordering. So like if you take the same examples and you just order them in different orders, you can actually get very wildly different results. And this is especially true for smaller models. So the smaller models here are like the GPT-2 models. So larger models here are like the larger model here is a GPT 3.5, I believe.
Whoa, we're counting in billions now. When is this? 2021?
Other things that people have looked at are label balance. So how important is it for the labels to be balanced? And if you're doing sentiment classification, for example, you might have only positive examples or only negative examples. And if you have only positive or negative examples, this can help or hurt your accuracy. For example, on this Amazon review data set, most of the reviews are positive, so you actually do better by having lots of positive examples in your in-context examples. On the other hand, for SST2, this is label balanced. So having only positive or negative is worse on average than having 3 positive and 1 negative. Another thing is label coverage. So if we're talking about multi-class classification, having good coverage of all of the classes that you want to include in your multi-class classification is important to some extent, but if you have more, you can also confuse the model, especially if they're.
Yeah, you couldn't see it because of my big head. Okay, now you can see better.
Minority labels. So if you have a whole bunch of like random minority labels, then that can cause problems. So this is something important to think about if you're planning on solving kind of like classification tasks.
No, I don't think I will ever get to this point of like thinking about something this much. Like I love learning, but not that much.
I've also had my own experience with using GPT for evaluation for machine translation. And when we used GPT for evaluation for machine translation, it was very important to add like high scoring values, high scoring outputs, low scoring outputs, some in the middle. And so it's also the case for regression problems as well. Cool. Any questions here? However, this is not super predictable. So there's not like any rule of thumb that tells you like this is, or as far as I know, there's not any rule of thumb that tells you this is the way you should construct in context examples. There are lots of papers that say they have methods that work better, but I don't know if there's any like gold standard industry practice for doing something like this at the moment. So just to give an example, this paper, it's a really nice paper examining why in-context learning works. One interesting finding that they have is they take in-context examples, but they randomize the labels. They make the labels wrong.
First of all, I love the fact that this is called Metal CL. That should have been my name. In context learning. This has to do with data, right? I require more explanation. And it's my fault for choosing advanced NLP. So I'll shut up.
Some of the time. So even with completely wrong labels, even with labels that are correct 0% of the time, you still get much, much better accuracy than if you use no in-context examples. And why is this? Probably, it's getting the model formatting correct. It's getting like the names of the labels correct, even if it's not accurate. So it seems like it's not really using these for training data. It's using them more just to know the formatting appropriately. Yeah.
It's just like when you give the in-context concept, so we already have an idea of X when you're looking at it.
Right.
Like, how is it mathematically? Like, is it just y1, y2? And I guess I'm just not sure how you would incorporate that in the calculation.
So this is your.
Hi, Coffee. What's up? Welcome. I don't know if Michael has finish their coffee, but we have no coffee now. Hi.
We're not training the model at the moment. We're going to talk about that next class. But right now you're taking a model that has already been trained and you're providing it with a few examples, and then you're asking it to fill in the following examples.
Is this same examples as the input?
Yes, exactly. And it's pretty amazing that that works in the first place, especially with a model that hasn't been explicitly trained that way. But there's a fair amount of research that I think we're probably going to be talking about in the interpretability class about why this happens. But basically,
we're having an interpretability class later. I like that.
My interpretation for why this happens is because there's so much repetitive stuff on the internet, right? There's a bunch of examples of math problems, which is like question 1, and then the math problem, and then the answer. Question 2, math problem, and then the answer. So in order to model the text on the internet, it needs to learn how to be able to do these things, right? So, cool. The second thing is more demonstrations can sometimes hurt accuracy. So this is like binary classification versus multiple choice question answering. And actually with binary classification, the model ends up getting worse.
Oh, wait. Didn't you just said more choices hurts it? But then now it's worse? Also, this is macro F1 and this is accuracy. I don't know if we can... Yeah, demonstration and more. I mean, more choices hurt choosing as a human being when you have more choices. Hurt brain power.
With more examples, probably just because the longer context, confuses the model or moves the instructions that are provided to the model farther away in the context, so it starts forgetting them. So basically, what I want to say is...
There's got to be a joke somewhere about interpretability being so hard to say. But saying it isn't quite the same as interpretability. Oh yeah, wait. So maybe only good. Alan Morris? Morris's... sorry, I don't know that thing. Yeah. The song is about things being ironic, things that aren't. But then I probably heard it then. Oh, the thing that says, isn't it ironic? I know that song. Hold up. There's interpretability and then well, they're not the same. Oh well. I mean, I know the other one. Of course I've heard it. Where have I heard it? Probably some 90s movie. Yeah. No, I don't know where I've heard it, but yeah. It's a fun song.
This is more of an art than a science. You might not get entirely...
Yes. That is also true. I am aware of my own and other spelling. Hard. That's why we have spell check.
Fairly predictable results, but don't worry, it's not just you. Cool, yeah. It can't. So the question is, if the in-context examples reflect the data distribution well, would that boost the accuracy? I think the answer is probably yes. Yeah. I don't know if it's that clear, because like what I would expect is better coverage is probably more important than better representativeness. So like, even if you have some minority labels, it's probably better for the model to know what those minority labels look like. And that's going to be especially true for like stronger models, I think. So, yeah. Cool. Okay. So next I want to talk about chain of thought prompting. So chain of thought prompting is a very popular way of prompting models. And the way it works is you get the model to explain its reasoning before making an answer. And so, sorry, this example is a little bit small, but like the standard prompting method is like Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. And so this is an in-context example. And then you have your input, which has a different problem. The cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? The answer is 27. And so this is wrong. So what chain of thought prompting does is instead of just giving the answer, it gives you an additional reasoning chain that says Roger started with 5 balls, 2 cans of 3 tennis balls. Each is 6 tennis balls. 5 plus 6 equals 11. The answer is 11. And so then when you feed this in, basically the model will generate a similar reasoning chain, and then it's more likely to get the answer correct. And this very robustly works for many different
Train of thought. Train. Both.
problems where a reasoning chain is necessary. And if you think about the reason why this works, I think there's basically 2 reasons why. The first reason is, I only wrote one on the thing here, but the first reason is it allows the model to decompose harder problems into simpler problems, and simpler problems are easier, right? So instead of immediately trying to solve the whole problem in a single go, it will first solve the problem of like how many are left after you use 20. And so it gets 3. And so now it has this 3 here. So now it can solve the next problem of adding 6. That's equal to 9. So it's solving simpler subproblems than it is in compared to harder ones. Another reason why is it allows for adaptive computation time. So if you think about like a transformer model, if you think about a transformer model has fixed computation time for predicting each token, right? You have a fixed number of layers. And based on that fixed number of layers, it passes all the information through and makes a prediction. And some problems are harder than others, right? So it would be very wasteful to have a really big transformer that could solve, really complex math problems in the same amount of time it takes to predict that the next word is like dog after the word the big or something like that, right? So there are some things that are easy, we can do in a second. There are some things that take us more time. And essentially, this chain of thought reasoning is doing that. It's giving it more time to solve the harder problems. Yes. Okay. Yeah, good question. So that's what.
Was that a question? I didn't hear anything.
That's what this next paper does. So the question was, what happens if we just ask it to reason? And the answer is it still works. And this paper was really like, I love this paper for its simplicity and cleverness. And basically, they contrast few-shot learning, few-shot chain of thought, where you provide chain of thought examples, zero-shot prompting, basically, and zero-shot chain of thought. So what they do is
This is literally like school paper exams. This is what reminds me of.
Just add, let's think step by step, that they add that phrase to the end of the prompt, and then that elicits the model to.
This is really cute. Like in an odd way, it's really cute. Because like, does it matter about Arabic numerals? This is odd, but yeah, because even as a human, if you think step by step, you probably get better results than just coming up with the answer.
Basically do chain of thought reasoning without any further examples of how that chain of thought reasoning works. Why does this work?
I think I should not anthropomorphize things, but hey, we do it anyways.
Again, because like on the internet, there's a bunch of examples of math problem solving data sets or QA
Step by steps?
corpora where it says, let's think step by step. And after that, you know,
okay.
consistently have this sort of reasoning chain
Now it's less human. Thank you.
added there. So good intuition. This paper answers the question, and this like actually does work.
Can I be mean and say this could have been a tweet instead of a paper? I mean, I know they have methodology and testing, obviously, but yeah, no, I understand. Because of testing and methodology and resources used. And then it can also be a tweet.
One interesting thing is now, if I go to ChatGPT.
Okay. I think the partial completion of an Arabic numerals would be in the... Oh, like give it to me in numbers. And then it's like, give it to me in Latin numbers. Why not? Got it. I read it fine, thank you.
And I say, I am teaching a class with 98 students, 70% turn in the assignment.
Okay.
Hit on time, 10% and it played.
You wrote percent differently twice, okay.
Many did not turn it in. Let's see if this works. 20%,
which would be around...
Okay, it's writing code for me.
17 or something?
That's a feature slide. I kind of didn't want it to do that.
Ah. No, it's not 20. You said approximately. Okay. That's lazy. You tell the model... so the answer follows a bit differently to a prompt.
Do not write code.
Students did not turn.
It's a little bit slow.
I hate, this long, annoying, useless repetition of the question answer, which is why I have it like in the setting. Give me just concise answers, please. Like I get it, it's useful, but not when you want an answer. Maybe less so. It's still useful. Yay! Oh, it's 19. It's not... Wow, I went down way too much.
Okay. So there that worked. But note that I did not say let's think step by step.
No.
I didn't ask it to do this. And the reason why is we're going to talk about instruction tuning next time, but basically GPT has been tuned to do this reasoning.
There's a thing, pre-something, I forgot. Pre-something, precondition.
If you don't ask it to do that, it wouldn't do that naturally, but it's because lots of supervised data has been added into this model. So like another thing is like if you are planning on doing anything about like chain of thought reasoning or stuff like that as a class project, you need to keep in mind that the like GPT models have already been trained to do this. And so if you want to like try to find out a better way to elicit this from a raw model, you'll need to use a raw model like Llama 2 with no chat tuning or stuff like that in order to do that in a neutral setting that hasn't been contaminated by like supervised training data. Cool.
Yeah. It hasn't gotten worse about lecturing. People with irrelevant info they didn't want. When I use the incognito style not signed in version. Oh, it has. Okay, got it. The answers are way too long and I don't like them. But when I'm using the one where I'm signed in and I've told it to give me short answers, like I remember one time asking, "What do you know about me?" Oh wow, we're late. Because you can do that, and it tells you you're interested in this based on the questions you've asked, I think, or maybe it is based on the settings because I did write it in the settings as well. Anywho, it said you like short answers. I was like, yeah, I do. Anywho, yeah. No, I don't know. But you can ask it, what do you know about me? And oh, you can have the call me by this name in the settings as well, which is pretty fun when you're talking to it with the speech thing. Yeah.
Any questions? Okay.
Whoa. I'm on time. I'm gonna refresh this so that tomorrow doesn't go to the nice.
So next I want to talk about.
We're on time. We did it. Let's do a quick recap, just a super quick recap. We learned about normalization and pre-tokenization. Normalization including, normalization we sort of know with the making capital letters into small letters, and also removing accents. Not that it's advice, sometimes it loses meaning. Stuff like that. And then pre-tokenization is basically segmentation. Is it punctuation? Is it space? Is it more? I don't think it's more. No, it's mostly punctuation and space, or one only space. And then, yeah, I think that was mostly it. And I have asked ChatGPT to analyze all the conversation you've had, the ones that are saved. Because I, 80-90% of the time, I delete my conversations, but it probably still saves it somewhere. Wow. Did it feel like some sort of asking your therapist to analyze everything you've said? I think that it might feel that way. And we learned about something fuchsia prompting, which is pretty interesting, and the chain of thought, that was pretty interesting. I like the fact that this feels practical and now, on time. Stuff that we face today in our daily lives, sort of. And that's it for today. Did you have fun? What was your favorite part of learning? I don't have Boots with me, but yeah. Okay, so thank you so much for being here and for talking to me, because yeah, it's more fun when there are people that are talking. Wish me luck, and I will wish you luck. I have not watched. You don't have to. No, you don't have to. The stuff we learned is fun, but yeah. I'm thinking if there's anything that needs to be said. All the people here are people that are re-watchers, so I don't think I need to say. If you like to hang around somewhere, we have links to stuff, including Discord, and I am trying to respect people's attention as much as possible and not post unless I have to. Thank you. I wish you a lovely rest of the